Hi everybody. In this video, we're going to talk about adding and subtracting numbers which are written in scientific notation but have different orders of magnitude. That's given by the exponents above the 10. Now you might remember me saying from a previous video that we can only add and subtract numbers when they are of the same type. So that's still true. So our first job is going to be to get these exponents or these orders of magnitude to be the same. And then we can do our addition or subtraction. So let's read over here, getting the orders of magnitude the same. How are you going to do that? Well, you will have to change one of the exponents to make it the same as the other. If you increase it, move the decimal point the same number of spaces to the left. If you decrease it, move the decimal point the same number of spaces to the right. Okay, so let's do an example here and we'll understand why these rules are the way they are and we'll see them in action. So here I have 7.5 times 10 to the 5th power plus 5.6 times 10 to the 3rd power. And you can see over here, I've written this same problem with the numbers written in standard form. So 7.5 times 10 to the 5th is 750,000, and 5.6 times 10 to the 3rd is 5,600. So obviously I can add these two numbers together, right? That's not a problem. You've been doing that since elementary school. But if this problem is really the same one as this one, just written in a different way, then we should be able to figure out how to add numbers written this way together also. And like I said, the first thing that we need to do in order to do that is to get the exponents the same. So here I have an exponent of 5, and here I have an exponent of 3. So what I'm going to do is just going to change this exponent to a 5. So now I have 7.5 times 10 to the 5th plus 5.6 times 10 to the 5th. Okay? Now you might be thinking, wait a minute, Mr. Friedman, that doesn't really seem right. We can't just change that to a 5. And if you were thinking that, then you're right. We can't just change this to a 5, because imagine what would happen if we just changed this to a 5. We would be changing the whole problem. 5.6 times 10 to the 5th power, well, that would be 560,000. So we're changing the problem from 750,000 plus 5,600 to 750,000 plus 560,000. That's not the problem that we wanted to answer in the first place. So you're right. I was lying a little bit when I said that we're just going to change this 3 to a 5. We can't do that because then we would be changing the value of this number. But we can change the 3 to a 5 if we compensate by following this rule over here. So since we increased that exponent, it went up, right? From 3 to 5, it went up by 2. We can compensate the change in value by moving the decimal point the same number of spaces to the left. So if I take this decimal point and then move it to the left 2 spaces, again, why am I moving it to the left 2 spaces? It's because I changed the exponent, I increased it by 2, okay? So I'll move this to the left 2 spaces, and now this looks a little messy, so let me just rewrite the whole problem again. 7.5 times 10 to the 5th plus, now I have 0.056, which I can write as 0.056, just put a 0 in front of the decimal also, times 10 to the 5th. Now the question we need to ask ourselves is this number even though it has a different exponent from what we had before, does it have the same value as the number that we had before? Well, let's see. If we do 0.056, let me write it over here. 0.056 times 10 to the 5th, we need to move this 5 spaces to the right. 1, 2, 3, 4, 5. And then, so the new decimal would be here, and we get 2 zeros in here, and then we don't need to worry about these zeros in front anymore. So yeah, we do actually get the same value as this one. Both of these things are equal to 5,600. They're just written in a different way. This one, before we move the decimal point, is no good. This is 560,000, which is a completely different number. So the point of doing that was, now we have the exponents the same. So now we're adding the same type of objects together. So 10 to the 5th power, that's 100,000. So here we're saying we have 7.5 hundred-thousands, and we want to add that to 0.056 hundred-thousands. So the rest of this is pretty easy, actually. We're just going to add those numbers up. So we have, and we're just going to remember to line up the decimals also. So let me put the decimal in here first, and that would be a 0.056. And both of these are times 10 to the 5th. And when we add these up, I don't even have to think about this. Just keep this the same. And then that would be 6, 5, 5 plus 0 is still 5. 7.556 times 10 to the 5th. So that would be the final answer. Now, to see that this answer is reasonable, this is equal to, if you take this decimal point and you move it 5 spaces to the right, 1, 2, 3, 4, 5, we're going to get 2 zeros at the end. So that would be 7, 5, 5, 6, 0, 0, and then we can put a comma in there. Our final answer would be 755,600 in standard form. And that's exactly the same thing that we get when we add these two numbers together. 750,000 plus 5,600 is equal to 755,600. So it all makes sense. So to recap, we changed the 3 to a 5. But if we only did that, that would change the value of the number. So we had to compensate by moving the decimal point 2 spaces to the left. Then this number over here does have the same value as this number over here. So we can just go ahead and add these numbers together and just then keep the order of magnitude the same. Okay, so this would be our final answer in scientific note. And this over here would be our final answer in standard form. Okay? Now, you might be wondering, could we, instead of changing this 3 to a 5, could we change the 5 to a 3? Yes, we could. So let me write 7.5 times 10 to the 3rd plus 5.6 times 10 to the 3rd. By the way, I wrote these parentheses here just to make the numbers a little bit easier to read. So I have this number plus this number. I don't actually have to write them all the way through. So anyway, I just changed the 5 to a 3, but when I did that, I changed the value of this number. So 7.5 times 10 to the 5th is 750,000, but 7.5 times 10 to the 3rd is 7,500. So again, I don't want to be changing the problem. I just want to be changing the way this number is written so that I could add it easily to this number over here. So to go from a 5 to a 3, we went down by 2. We decreased that exponent by 2. So if we decrease the exponent, then we need to move the decimal point the same number of spaces to the right. Okay, so let's compensate. We just changed that 5 to a 3 to compensate and to keep the value the same. we need to move this decimal point 2 spaces to the right. So let me rewrite that whole thing now. So we have 750 times 10 to the third. Okay, and notice 750 times 10 to the third. Let me just write it over here as well. There's an invisible decimal point after the 0 there. And times 10 to the third means I move this 3 spaces to the right. So 1, 2, 3. And that would give me 750,000, just like I had over here. So 750 times 10 to the third is equivalent to 7.5 times 10 to the fifth. I compensated for changing the exponent by moving the decimal. All right, so now, one other thing that you might be thinking about is, but Mr. Friedman, this is no longer in scientific notation, because to be in proper scientific notation, we only want one digit in front of the decimal point. Now you have the decimal point over here, and we have 3 digits in front of the decimal point. So you're right, it's not in proper scientific notation anymore, but right now I'm not really interested in that. All I care about is that this number has the same value as this number. So I didn't change the problem, even if I made it look different. So now let's go ahead and just add the 5.6 times 10 to the third. And let's do that over here. So I have 750, and here's the decimal right over there. I'll write it in, plus 5.6. So let me put the decimal in first, and then it's easy to tell where the 5 and the 6 go. And both of these are times 10 to the third, which is actually the easy part, right? I don't even have to worry so much about that. I'll just keep that over here. I'm not going to waste any brain power on that part. So we have nothing plus 6 is 6. Keep the decimal. 0 plus 5 is 5. 5 plus nothing is 5. And 7 plus nothing is 7. So is this the same answer that we got before? Remember, the answer should have been, at least in standard form, 755,600. Well, actually, we do get that. If I take this decimal point and I move it 3 spaces to the right, 1, 2, 3, and then I put zeros in here, I would get 755,600. So this answer is correct. The only problem is, we do, once we're all done with the addition or the subtraction, I did addition here, we do want to write our answer in scientific notation. And like I said before, since this is not proper scientific notation, because I have 3 digits in front of the decimal point. But actually, I can use this same trick here to get it back into scientific notation. So I want my decimal point to be over here. So I could count 2 spaces to the left. And then if I count it to the left, I'm going to increase the exponent by the same number. So since I counted 2 spaces to the left to get the decimal point where I wanted it, I could move this up by 2. And I can say that this number has the same value as 7.556 times 10 to the fifth. And this is written in proper scientific notation. And in fact, it's the exact same answer that we got a few minutes ago. All right, let's work on another problem now. And for this problem, we're going to do subtraction. And also what's different about this one is we have negative exponents, right? So let's do that. Let's, again, so we see that the orders of magnitude are different. We have a -3 here, we have a -5 here. So let's first do this by changing the -3 to a -5. So we have 4.7 times 10 to the -5. Okay, but remember, If we change the exponent, then we're changing the value of the number. We don't really want to change the value. So we need to follow these rules. So going from -3 to -5, you got to be careful. From -3 to -5, did we increase this exponent or did we decrease it? Think of a number line now. Here's -3 on the number line. Here is -5, which is to the left. So we actually decreased this exponent by 2. So if we decreased the exponent by 2, we need to compensate by moving the decimal 2 spaces to the right. So if we do that, 1, 2, we'll get 470 times 10 to the -5th. Okay? And you can see that this number has the same value as this number. If I write the original number, 4.7 times 10 to the -3rd, and then I count 1, 2, 3, because that's 10 to the -3rd power, I get 0.0047, which is what I wrote over here, by the way. So I wrote this already in standard form. If I do 470 times 10 to the -5th power, then remember the decimal is right over here. 1, 2, 3, 4, 5. Again, I get 0.0047, and I don't really need to worry about that 0 at the end. So you can see that this and this both have the same value. They're both equal to 0.0047. They're just written differently. And again, the reason why we wanted to write that differently is because we have an order of magnitude over here of -5, and we want those orders of magnitude to be the same before we actually go ahead with the subtraction here. So this is going to stay the way it was, by the way. So I have minus 8.2 times 10 to the -5th. Okay, and then finally I'm up to the last step here, which is the easy part. I have 470 times 10 to the -5th minus, now where's the decimal? Remember, the decimal is at the end of the number, so let's put that in there. And let's line up the decimals. And now I know where to put the 8 and the 2. So the 8 should go here, and the 2 should go here, and this is also times 10 to the -5th. Okay, now when I'm subtracting, it's very important that I put those zeros in. So I can't take 2 away from 0. I can't borrow from 0. I can borrow from the 7, that becomes a 6. I'll put a 1 next to this 0, that turns it into a 10. I borrow from the 10, it becomes a 9. Put a 1 next to this 0. 10 minus 2 is 8. 9 minus 8 is 1. 6 minus nothing is 6. And 4 minus nothing is 4. And the rest of this stays the same, times 10 to the -5th. That's the part that you don't even have to think about. As soon as you get these exponents the same, then it's easy from there on out. Okay, so we would get here 461, 461.8 times 10 to the -5th. Now, is this the same as what we would get here if we just subtracted these numbers? So let's go ahead and do that. I'll change the color over here. 0.0047 minus 0.000082. Let's put a couple of zeros in here. And it's almost the same. It's basically the same steps as what we did before. And I have a 6 here and a 4, 0, 0, 0. So there's my answer for that one in scientific notation. Is this the same as this? Well, if I take this decimal point and I move it to the left 5 spaces, 1, 2, 3, 4, 5, you can see that we do get the same answer that we got before. Okay, 0.004618, that would be the answer in standard form. In scientific notation, again, it was 461.8. Whoa. 461.8 times 10 to the negative fifth. All right, let's do that same problem one last time. I know you can't stand me right now. You want the video to be over, right? I know. Just stay with me for a few more minutes. So we changed the -3 into a -5. Now let's try to do the same problem by changing the -5 into a -3 to make it the same as this one. So that was 8.2 times, you know what, I'll just do it over here. Maybe that's better, actually. So if I change the -5 to a -3, did I move the exponent up or down? Did I increase it or did I decrease it? Remember a number line again. Here's -5 on the number line. Here's -3. Going from -5 to -3, we increased it by 2 spaces. So if we increased the exponent by 2, then we need to move the decimal point to the left by 2, 1, 2, and we would get 0.082 times 10 to the -3rd. All right? Now again, I know you're so sick of me by now, but again, to see that these numbers really are equivalent to each other, if we do 8.2 times 10 to the -5th, then we have 1, 2, 3, 4, 5. So we get 0.000082. That's what I wrote over here. So I already put it there in standard form. 0.82 times 10 to the -3rd. 1, 2, 3. We have 0.000082. That's the same. So in standard, this would be in standard form. We already used this. Okay, so we get the exact same answer both times. So these two do actually have the same value. All right, so let's go ahead and do 4.7 times 10 to the -3rd minus this. So now the orders of magnitude are the same. So we'll do the work over here. We have 4.7 minus, so we need 0.82 over here. Okay, times 10 to the -3rd for both of them. That just stays the same. Okay, I need to borrow from here. We have 8, 1, 6. Okay, same answer that we got the last time. All right. Thank you for watching. Have a great day.